Okay, YouTube, in this video we're going to explore the concept of a mathematical sequence. And I just basically want to comment on the fact that when we use the word sequence in real life, it kind of means the same thing that we mean in math. And that is to say that if you had things that occurred in order, such there was like a first thing, a second thing, a third thing, a fourth thing, da 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 da, that would be a sequence of things. When we talk about a mathematical sequence, we mean kind of the same thing. There's a set of numbers, a sequence of numbers, if you will, that occur in order, such that there's a first number, a second number, third number, and so on and so forth. So what I want to do is kind of explore the idea of a sequence through a very famous mathematical sequence. We refer to this as the Fibonacci sequence. And we say it's this set of numbers that you see here. You may have seen this before. If you haven't seen it before, it is just this sequence of numbers that starts with a 1, got another 1 next door, and then we say the next number is 2, then 3, then 5, then 8. And in terms of looking at patterns here, you might be able to infer what the pattern is. If we get up to 233, like what would come next. There are typically patterns that occur with these sequences of numbers. We often look at it here. So we say we think of the Fibonacci sequence as a function, really, and we say that the terms of the sequence. Now, when we refer to the terms of the sequence, these individual things are referred to as the terms of the sequence. So we're going to make a little note here. These are the terms of the sequence, and they are just separated by commas. But basically, each thing here is its own individual term. And we just refer to the one here as being the first term, this other one as being the second term, and so on and so forth. And then we typically say all the way out to the nth term of this thing, which is some undefined, not undefined, but like arbitrary term. Could be any term. But we say that these are the terms of the sequence, and they are the range of values for a function f whose domain is the set of positive integers. That is to say that if we look at this domain, is basically the term number, and that's what I want to write here, which term you are at. And if we look at the range is the term value, like what that term actually equals. What you can see here is that we have our numbers in our Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13. And what we're really saying is that the first number is 1, the second number is 1, the third number is 2, and fourth number, and so on and so forth. But what we're really mentioning here is that with respect to the terms of the sequence, if we look down here, we could refer to this as kind of like a function where we say that when we plug in 1, I get 1 as an output, or when we plug in my second term, I get 1 as an output. In other words, what we're doing is we're plugging in the term number here, and I'm going to refer to this as n in general, and we're getting a term value. And so we're going to say term number goes into our function, term number, and what spits out is the term value. So we have that as kind of like an XY type of relationship. So that being said, what I would like to do is essentially point out that when we refer to things in function notation, we refer to this as like f of x equals some y value, but we have input output. You plug in a 5, you get a 5, you plug in a 6, you get an 8, blah, 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 blah. Basically, what we can see here is in sequence notation, we represent the same thing elsewise. We'd say that a sub 1 is equal to 1. Or that is to say that this right here, we're going to refer to this a sub 1 as the first term in this sequence A. We're going to refer to A2 as the second term in the sequence of A. And we could go all the way out here. We say this is the sixth term in the sequence A. But you'll notice that in general, instead of an f of x, okay, instead with sequences, we say that this is a function right here. Function notation is f of x. We would say that sequence notation, we represent the very same thing just in this fashion. We typically use a letter like A and then a subscript n to kind of represent this. And sometimes you see that textbooks will write it a of n. But basically it's a function, and what we're saying is the only difference between a function and a sequence is that the domain of this, and I want to be clear on this, the domain is continuous. Domain is continuous. And what we mean by this is that it can be decimal. If you want. Decimal, for example. That's basically what I mean. It doesn't have to be a decimal. It could be something besides a decimal, but basically it's continuous and can be a decimal value. Whereas with the sequence, we just refer to the domain as being, domain is the set of counting numbers. And by counting numbers or natural numbers, we mean those starting at 1 and going up by the things on your hands. So we say 1, 2, 3, 4, 5. And what we're going to say is this. Sometimes includes 0. So if our domain is basically the term number, sometimes we have what we call a zeroth term. And in this particular case with the Fibonacci sequence, we don't. So with respect to the pattern on the sequence, if you haven't seen it yet, what we see here is a situation where if we took 1 plus 1, we would get 2. Or if we took 1 plus 2, we would get 3. Or if we took 2 plus 3, we would get 5, and so on and so forth. This pattern you could see of sequence of numbers here isn't just 6 terms long. You could see that we could just keep representing this over and over and over again. So when we look at this notation a sub n, the sequence notation that's just like function notation, we say that it represents the nth term or the general term. Now you're going to not hear me refer to this as a general term. I'm always going to call it the nth term. That's what you typically hear, the nth term of a sequence. But we say the entire sequence is represented by this set of numbers that has commas in between. It's a sub n, and we treat it like a function. So with respect to sequences, let's go ahead and take a look at what if I'm going to define a sequence here and write out some terms of a sequence using its rule, like you see a couple rules here. So we say that first of all, an infinite sequence, a sub n, that's how you would read it, a sub n or a of n, is just a function but whose domain is the set of positive integers. And remember, we refer to these as the counting numbers. And the counting numbers, just to be clear on this, are numbers that start at 1, 1, 2, 3, and so on and so forth. That's the domain. That's the numbers we get to plug into it. But we say the function values or terms in our function, these things separated by commas of the sequence, are represented by these. And these right here, we're going to represent these. These are the range. Okay, so we have the range of the function is just the term values. So we say sequences whose domains consist only of the first n positive integers are called finite sequences. So what we're going to do is we're going to distinguish between infinite and finite. Right now, we're saying that this ellipsis right here would indicate infinite sequence. And an infinite sequence is one that could extend on forever, remember, like our Fibonacci sequence. That being said, though, if we only include the first n terms, that's what they're saying here, if the domain only consists of the first n positive terms, then we have a finite sequence. And we say that a finite sequence must have a last term, and I'll put a little Oxford comma here, and we're going to write the last term as a sub n. It could be b sub n, c sub n. Just know that you can use other letters. In this video, we're going to use a sub n. So what I want to do in this video is essentially this. Write the first 4 terms of the sequence whose nth term or general term is given by this. So when you look at this, let's do this as, for the sake of notes. You can see that this right here, this is y equals 2x plus 5, or this is just a linear function if we graph it as a function. When we graph it, though, when we represent it as a sequence, though, we say a sub n is 2n plus 5, where n is our term number. So what we're going to do is we're going to do this. We're going to say a1, a2, a3, and a4. We're going to write this out. We're going to show our work on all of this, but we say 2n plus 5. Really all we're doing is this in every possible instance. We're going to take 2 times our input value, and then we're going to add 5 to that. So in this case, we'd say our first term, we would just plug in a 1. We say 2 times 1 plus 5, well, that'd be 2 plus 5 is 7. 2 times 2 plus 5, we would say 4 plus 5 is 9. If we looked on to the next one, we say 2 times 3 plus 5, well, you get a 6 plus a 5 is 11. You can see this is going up by 2 every time. Matter of fact, that's really kind of an important thing. When we look at linear things, that plus 2 is serving as kind of like our rate of change or our slope. So you can see that that slope appears up here just like it would with a line, except for that our term values are what we're spitting out here. So when we write this, the important thing is we actually write it like a sequence, and the first 4 terms are these: 7, 9, 11, 13. And we just put a box around this. We say this is the first 4 terms of the sequence defined by this rule. So moving a little bit more quickly on this next one, we say, well, the first 4 terms, we could say we want A1, we want A2, A3, and A4, the term values for our first 4 terms here. So when we look at a fraction, I'm just going to give you some advice here. What you do is I would evaluate just all the top numbers first and then all the bottom numbers. So in this particular case, we're going to get -1 to these powers here, -1 on top. I'm just going to go ahead and fill this in across the board. Except for our first term, we're plugging in a 1 up here. Second term, a 2, 3, and a 4. So we're going to simplify all of this. But for the bottom here, we get 2 to the nth power plus 1. So I'm just going to write my 2 to the power plus 1, 2 to the power plus 1, 2 to the power plus 1. I'm going to go back and insert my powers here, 1, 2, 3, and 4 for our first, second, third, and fourth terms respectively. So when we simplify this, what we're going to get is essentially this. On the top here, Let's go ahead and write those all in. On the top, we're going to get a negative 1 to a power, which really makes this negative 1 to the first is negative 1. Negative 1 to the second is a positive 1. Negative 1 to the third is a negative 1. Negative 1 to the fourth is a positive 1. You see an alternation in sign. And for the bottom here, we get 2 to the first plus 1. Well, that's going to be 2 plus 1 is 3. 2 to the second plus 1 is 4 plus 1 is 5. 8 plus 1 here would be 9. And here we get 16 plus 1, we get 17. So we can see that this is the first 4 terms of the sequence right here. So a sequence really defined just like a function, but whose domain is a set of natural numbers. And we could just use that rule for the nth term to write out any term in the sequence we want. Cheers.